So for 1A, it says to determine the total mechanical energy of the satellite at point A, assuming that the gravitational potential energy is 0 at infinity. So if it is 0 at infinity, then we know that the total mechanical energy, E total, will have both kinetic and gravitational. It's no longer the whole idea of gravitational energy being 0 on the surface of the Earth. So in this scenario, we're going to use our normal 1/2 mv squared for kinetic energy. Gravitational energy is in your physics equation sheet, which is G, mass of the Earth, mass of the satellite over radius. And then we're just going to go ahead and plug in the values. 1/2 times 2,000 times the velocity is 7.1 times 10 to the third squared minus 6.67 times 10 to the negative 11 times mass of the Earth, which is 6 times 10 to the 24. And then I'm going to squeeze in the mass of the satellite here, 2,000, all over the radius, which is 1.2 times 10 to the 7th. And I'll go ahead and let you do all that calculation. To break it down, you should get 5.04 times 10 to the 10 minus 6.67 times 10 to the 10th power, and your final answer is negative 1.63 times 10 to the 10 joules, because we are talking about total energy. For part D, we're determining the angular momentum of the satellite. The equations we have for angular momentum, which is represented by capital L, is momentum cross radius, or inertia alpha. And so in this scenario, we're not given the inertia. We do know the acceleration due to gravity, but what we do have is mass and velocity, and we have the radius. And we can see here at this position, the radius and the velocity are perpendicular, and so we can just use mv times r. Mass again is 2,000. The velocity is 7.1 times 10 to the third. And then the radius is 1.2 times 10 to the 7th. And that ends up equaling 1.7 times 10 to the 4th power. And our unit here is kilogram meters squared over seconds. All right, so for part C, it says, what is the minimum speed of the satellite at point A in order to escape from Earth? The equation is given to you in the notes, but I think it's always good to go through the practice of deriving the equation. And when we think about this type of problem, we want to think about conservation of energy, where we start off with kinetic and gravitational, and then we always talk about this concept that energy is equal to 0 at infinity. So if we truly had conservation of energy, this should equal 0, wherever it is in the orbit of the Earth, or within the Earth, it should always equal 0. So what we're going to do is we're going to take our kinetic energy equation and our gravitational energy equation on the surface and solve for our velocity. And in this scenario, velocity is equal to the square root. What's nice is this m cancels out. And then if I bring the 2 over to the other side, I end up with I have to bring this over to the other side first, which makes it a positive, and then I can multiply both sides by 2. So sorry if I'm going through this math a little quickly, but hopefully when you go through the basic algebra, you'll get this equation, which again is something that you are right out of the bat given in your notes, but again, good to go through the practice of deriving it. Otherwise, you are going to want to memorize it and put it into your calculator if that's a possibility. So plug in the values, plug in the mass of Earth, and then the radius at that point, which is that. And then when you plug it into your calculator, you get 1.65 meters per second. For part D, we've got the satellite on the opposite side of Earth, and it's the furthest point from Earth. Its radius is 3.6 times 10 to the 7th. Ignore the notation here. And it says, determine the speed of the satellite at point B. Well, what we have here is conservation of momentum, because we know that, actually we learned about this in the last unit when they talked about Kepler's second law, that the momentum at point A and actually anywhere in its orbit is going to be conserved, and so they're always going to be equal. So if we take the momentum, multiply it times the radius, it goes back to Kepler's second law, stating that an object will move faster at a position closer to the Earth and slower at a position further away. So here we can check that theory and see if our velocity at B is going to be slower than the 7.1 times 10 to the third. What's nice is we already calculated the initial momentum here, which is 1.7 times 10 to the fourth. So that's going to be our initial momentum. And the final momentum is angular momentum is momentum cross radius, which is mass times velocity cross r. And what's nice is we want the perpendicular component, which it's already perpendicular. So it'll be the mass of the satellite, 2,000. We're solving for VB, and the radius is 3.6 times 10 to the 7th. So we've got 2,000. Radius is 3.6 times 10 to the 7th, and we're solving for velocity here. And if you divide everything over, velocity ends up being 2,361 meters per second, which translates to 2.36 times 10 to the third power. And if we compare that to the speed at point A, it is significantly slower. So that seems to check out well, and this would be your final answer for part D.